So very briefly, again, I'm going to talk a lot about some mobile sampling that we did in Pittsburgh. We were focused on components of particulate matter, so black carbon and particulate-bound PAHs, polycyclic aromatic hydrocarbons. We looked at a suite of VOCs with the GC, measuring some criteria gases like NOx and SO2 and CO2 should be on there, and some filter sampling, again, to get at PM components. And I'm going to describe, in this first part, I'm going to talk about, well, throughout, I'm going to talk about sort of two challenges that arise from mobile sampling. The first is that unless we're really willing to sample nonstop all the time, you're going to get a small number of hours at any given location. And that's just sort of inevitable, right? We only have one mobile lab that we can deploy at a time, right? It can only be one place at a time. And then one is a function of some statistical modeling that we're going to produce from this, is that these models are generally have poor transferability. So you can't build a model for Pittsburgh and apply it to Minneapolis. You can't necessarily build a model for one part of Pittsburgh and do it and apply it in another part. So we did this sampling in two phases. And a reviewer asked recently, we were sending paper, we were responding to comments, and the reviewer asked why we did it this way, and the honest answer is because we got funded to do this green part first, and then they liked us enough that they gave us money to go to the outside. So the green points are what we call our phase 1 sampling domain, and that was in 2011 and 2012. And then the blue points are what we call our phase 2 domain. And so the phase 1 domain focuses on the city of Pittsburgh, which is in the center, and then an industrial area to the northwest, and an industrial area to the southeast. Most of phase 2 focuses on areas that are more suburban, though overall there are 70 sites and there are 6 repeats, so that we could sort of evaluate so mostly we're looking at spatial variation, a little bit of the temporal variation at the overlap sites. And so we can sort of classify these sites any number of different ways. And one sort of obvious and simple way is to group them based on whether they're classified as a low traffic site or a high traffic site. And then this is one example where it's sort of a macro sense, this mobile sampling gets us good understanding of the spatial variations. So we're looking at black carbon aerosol here. So this is basically the reason that this plume is visible. So you get black carbon a lot from diesel vehicles. You get it also from industrial processes, and those are important in our region. And so clearly we see that you have higher black carbon at high traffic sites than low traffic sites, though there's a lot of overlap in these box plots because we have a high regional background from the industrial sources. Now again, there's this inherent challenge, and UTAN published a paper on this last year, where if you want to get if you want to score how accurate you are relative to the true annual average concentration at a particular spot, that depends in part on two things. One, how variable the data is, right? So if you fit sigma for a log normal. And then two, how long you're sampling there. And in general, background sites are more variable than, background sites are less variable than urban sites. And when, the particular sampling strategy that we used here is, we see a lot of the time we're less than 50%. Maybe at background sites we can be reasonably accurate. So I'm going to describe next a couple ways that we can leverage the fact that we're good at the spatial patterns and how we can overcome this sort of inaccuracy in the annual average. Though it's worth pointing out we're not sort of equally bad at determining the annual average for all different pollutants. So if we compare our mobile measurements of PM 2.5, which I'm showing here on the right in red, to all of the reference monitors, the annual average, so we were only sampling in summer and winter, these are running all year, we're statistically significantly higher, right? We're definitely above that. Though, so this could be just a matter of, we don't have enough hours, or we're sampling sort of at times of year that don't give us something that's close to the annual average, or it could be bias. If I were to change this to the common time periods, right? So if I was comparing like time periods, we actually don't have a bias. So we believe our sampling is not biased, we just sort of aren't at certain locations enough for certain species to get a good representation of the annual average. However, for stuff like PM 2.5 organic carbon, which is less variable over the course of the year, we actually do a better job. Now, what I showed on the last two slides, they take all our data and do a bunch of averaging, which frankly I hate doing, right? Why am I driving around collecting data at 1 Hertz to take this giant average, right? That's sort of silly. So And one advantage that we have is that since we're sampling at high time resolution, we can pull out individual events. So here I'm showing an hour's worth of data, and this is CO2, and we see lots of individual spikes. And each of these individual spikes is an individual vehicle. And I'll point out that our inlet is on the roof, so it's not that we're just sort of sucking direct exhaust as people drive by us. These are plumes. They have at least a few seconds to sort of advect up to us. And so note, in this particular hour, there's, I forget how many, there's 20 or 25 or 30 individual spikes that we can resolve for CO2. Now I'm going to add on to that, so this is the same CO2 data on the bottom. Now this is black carbon data and particle-bound PAH data for the same time period. And so you see there's a big chunk, with all of these spikes, there's no change in black carbon, no change in PAHs, right? And so overwhelmingly, these are automobile emissions. And that we see for some subset of these CO2 spikes, and they're not necessarily higher than the rest of the spikes, we get big responses for the other species. And essentially, the situation is what I'm showing here on the right. What we're seeing are emissions from diesel vehicles. Well, overwhelmingly, these are emissions from diesel vehicles, and we're able to pull them out. And TAM published this analysis last year. And so what we do is we basically treat all of our data as a combination of these spikes. These high HEV here is high emitting vehicles, and they're imposed on a background that we're calling our non-plume background. And so basically what we do is we treat this like a chromatogram. So we draw a baseline, which in here is the blue line. Everything below the blue line is our non-plume background, and everything above it are these plumes. And one thing we can do is we can do a very simple parameterization of the total contribution of these plumes as a function of the average daily truck traffic at the individual sampling sites. And this is just the data that's available. The average daily truck traffic is the data that's available from the Department of Transportation. Right, and we see a good relationship there. And so we're going to use this relationship to build a spatial model that takes advantage of this, that has this two-layer structure. It's going to have a plume layer and a background layer. And for the plume layer, what we're going to do is we're going to take that relationship I showed 2 slides ago, and then we're going to impose basically a functional form to it. So lots of people have looked at how pollutants disperse away from roadways. And so this, I'm citing one particular review from 2010. This is not our work. And there are a lot of species that if you start at the edge of the roadway and then by the time you get out to 100 meters away, things have decayed back down to background, right? And so we impose this particular functional form, and we apply that, that regression that I showed a few slides ago. And so now I'm showing for our phase 1 domain, and the boundary of the phase 1 domain is the heavy black line. This is our plume layer, right? So each individual line is a different roadway. So I'm highlighting here, there's a highway. All of the sort of blue little spaghetti are the lower trafficked roadways. So we're seeing, lower impacts on low trafficked roadways. The, highways, we have a higher intensity of this plume layer. So one way we can test this is our phase 1 domain. Recall that our phase 2 domain is sort of to the outside of this. So we can apply this this plume layer to the phase 2 domain. And when we do that, we find out it works pretty well. So I'm showing here our measured plume layer in our phase 2 domain, and then the prediction. And you see most of the points cluster around the 1-to-1 line. Right? So this is an example of this particular plume layer being transferable. So we applied it, and it worked. The 3 colored points are outliers, and I've colored them because we feel like we understand why those points are outliers. So for instance, this red point was a sampling location that was also, it happened to be adjacent to a railroad and the busway, so a bus-only highway. And those things are not in the plume layer of our model, so we would expect to underpredict there. And likewise, at the blue point and the sort of greenish point, we feel like we understand why we're predicting poorly there. But overall, the plume layer seems to be transferable. So our non-plume background layer, we're using just a typical land use regression. And so that's a method where you relate different land use variables, so whether the land is zoned industrial or it's a park or what have you, to the measurements. And when we do that, we get a picture that looks like what I'm showing on the right. And there's a lot going on there. I want to point out two of the variables that are important. One is elevation. So, and it has a negative coefficient, meaning that we have higher concentrations the lower down you go. So anyone who's ever watched a football game from Pittsburgh that's broadcast on TV, they talk about the confluence of the three rivers and they show the incline going up and down. Well, the rivers, basically, we're located on a plateau and the rivers have carved out a valley that's on the order of 100 meters deep. So pretty quickly, as you go from the riverfront up to the surrounding plateau, you have a very large change in elevation. And a lot of the highways are in the river valley, and a lot of the industrial areas are in the river valley. And basically, everything we measure is systematically higher in the river valleys. So we would expect this particular variable to show up. And then the other one that I want to highlight is fractional industrial land. So a few people were surprised. We still actually have one active steel mill, and there are a couple other big industrial sources in Pittsburgh. So most of them have closed, but there's still a number of them around. And they're important emission sources, and that shows up as well. And so when we put the two together, right, so now we take our non-plume background and we're adding this plume layer on top of it, we get the picture that I showed earlier in the talk. Right, and we see all these features. So we see the roadways, and they're sort of these narrow line features that very quickly fall off to sort of background levels. The river valleys are pretty clearly laid out, and then these industrial areas are sort of these red blobs. And so what we want to do with this, and I should point out these variations are pretty large. So you can go from a background concentration that's 0.5 microgram per cubic meter, within a few hundred meters of the roadway, get up to something that's like a factor of 3 higher in concentration. So very big spatial differences over relatively small scales. And so I'm going to briefly show two applications that we have of using this data. One is we can look at all of the single-family homes in our phase 1 domain, and we classified them based on income, and these are income deciles. So this is the lowest income, and 10 is the highest, and roughly the lowest income decile are people living below the federal poverty limit. And what we see is that black carbon, if you follow the central tendency here, the medians, concentrations decrease as you go up in income, which is maybe not surprising. What I think is a little bit surprising, though, is we can decouple the background layer and our plume layer in our model. And if you look, the plume layer is basically constant across all of these income strata. And what's really driving the difference in concentration is the background. And so that's proximity to industry and whether these people are living in the valley or up on the plateau. Another thing we can do, and this is work in collaboration with Colorado State, is you can basically feed our map into the dose response function and get an estimate of sort of the public health burden of this exposure, right? And so this shows, the colors here show sort of additional risk of dying relative to the cleanest census tract. So this is the cleanest census tract. So this is relative to that census tract, what is the additional risk posed by exposure to black carbon? And their estimate comes out to about 1.5% of deaths per year in the county, so 150 out of 10,000. I'm not going to stand here and say, yes, it is exactly 150, and this person died and that person didn't from that particular exposure. But I think it's very useful to sort of put a number on it to sort of scope what to get a scope of what this means in sort of a public health context. So I'm going to take one slide aside here. So a lot of my work has involved organic aerosol, and up until about 2 weeks ago, I had no project that had to do with organic aerosol, and as I told Julian at dinner last night, that made me very sad. But one thing I did not cover, we did not apply this method to organic aerosol, and part of the reason is the black carbon fall-off is largely driven by mixing and deposition. Organic aerosol evaporates. So this is some work done by my student Shang Li. He was measuring organic aerosol in a traffic tunnel. So he's just heating it in a thermodenuter, which is essentially a heated tube, and looking how much evaporates. And heating, most of it evaporates when you heat it. A similar thing happens when you dilute it, is that a bunch of it evaporates. And one thing we're interested in going forward, is how this plays out in these near source regions. All right. So one way we can deal with sort of the strengths and weaknesses of our data is to do this plume analysis. The other is to start linking sites together that have some sort of commonality. And I'm going to show an example here where we've now again, the sampling individual sites are indicated by the dots. And now what we're going to do is group them based on these different regions. And basically, these are areas that have similar land use. So for instance, one region is the downtown region. You know, this up here is a sort of newer suburban, lower density suburban housing. This is higher density suburban, an industrial area, and an industrial area. And one thing we find if we look at benzene, and this result, when Bob brought this to me, surprised me, because if you say benzene, there are still a lot of people who say their first response is it's from cars, right? And cars used to emit a lot of benzene, and there used to be a lot of benzene in gasoline. But if you look actually on a per unit fuel basis, modern vehicles don't emit a lot of benzene. But again, there's still many millions of cars, so they're an important source in aggregate, but individual cars do not emit a lot of benzene. And if we look at the spatial pattern of benzene, we see that in downtown, which is clearly the area with the highest traffic density, especially twice a day at about 8 a.m. and 5 p.m., it's not the hotspot for benzene. The hotspot for benzene is actually in this part of Pittsburgh, which is, yay, that's where I work. And then there are other higher areas sort of in more industrialized areas. Similarly, for toluene, we get a similar picture, right? That the industrial areas and these areas in the eastern part of the city are higher than downtown. And then if you get up into the northern suburbs where the population density is sort of the lowest in our domain, they tend to be the cleanest in both cases. So we want to understand what's going on here from a source perspective. And one tool we can use to look at sources is called a ratio-ratio plot. And so the idea is if you take 3 species you're interested in that all can have a common sort of set of sources. So I'm showing xylene isomers, toluene, and black carbon. And so these are all things that you can get from combustion systems. And you normalize 2 of them by the third. So I have toluene to BC and xylene to BC, and I have a bunch of data. And this data more or less aligns along a line. And what this allows us to do is if we want to do a source apportionment, we can say, well, I just need a source down here and a source up here, and then a line through that, and any of this data can basically be described as a linear combination of those sources, for the most part. Or alternatively, I can have 3 sources and draw a triangle, right? And again, I can come up with a way to describe all of those individual points. So I'm going to do the same now for we're going to use a ratio-ratio plot of toluene to black carbon and benzene to black carbon for our VOC data. First, I'm going to point out that all of the yellowish gold diamonds are individual point sources. So these are industrial type sources. And then the red, this is a gasoline fleet profile and a diesel fleet profile that we've determined from our traffic tunnel measurements. And the dashed line connecting them is the mixing line between them. And note that these are both log scales, right? So small differences between points actually could be pretty big. And so if we put all the data, we see that a lot of it falls along this traffic-based mixing line, but there's also a lot of scatter away from it, right? This is, and we're interpreting this to be the influence of these point sources. And then, of course, there's this whole chunk of data that's up here, sort of up and to the right from gasoline, that you can't describe as being from traffic. Now, we would expect our expectation would be that downtown is dominated by traffic, and in fact, that seems to be the case, right? There's the downtown data, which are now the cyan points, are much closer to the red mixing line than sort of the overall data set. However, again, I said downtown turns out not to be this hotspot, and that's sort of surprising to us. And if we look at where the high concentrations occur, some are over in this industrialized area, and some are in the eastern part of the city, and then the rest are sort of distributed about. And there's not necessarily, aside from these sort of 2 areas, it doesn't seem like there's a lot of sort of rhyme or reason to where the super high concentrations are occurring. But if we plot them in ratio-ratio space, and now the green ones are the top 1% and the pink ones are the top 5%, we see that overwhelmingly they're up here beyond sort of the gasoline fleet profile. And this is sort of puzzling to us. So we don't know what the source is. So what this means is there's probably a source somewhere up here, right? And it may be that one, but if I recall right, this is a small source. So this would we're getting high concentration events from some source that has really high VOCs and low black carbon emissions. So our typical interpretation of something like that would be to say it's like fuel evaporation, right? Like this is gas stations where you have a lot of VOCs and a little bit of BC emissions from the vehicles that are operating around the gas stations. But that's sort of a distributed source, or it could be like an area source, like a sort of a tank farm. But you would not expect that sort of source to drive the highest concentrations that we're observing.
I have a question. So
yeah.
Each of those points, like the green triangle or green stars, is a location?
Yes.
And can you remind us how much time went into each location's measurements?
So now I don't remember. So we would every time we visited a location was an hour, and we would visit the locations multiple times. And I don't remember if these are individual 15-minute samples or if these are averaged up to 1 hour. I don't remember. Yeah. So it could be that these are a sub-process. So some of these, this is the overall emissions from this source, but of course that particular source has many sub-processes. And it could be possible that it's one of those sub-processes, but we're still trying to figure out what are driving these sort of highest concentration events. Now we know that in general industrial sources are important and could be, I don't know, I think they're the most likely reason, but we don't have sort of a lot of data to back that up yet. We've done a little bit of dispersion modeling. So right here I'm showing the modeled sort of the typical plume from this industrial area along the Monongahela River, and it sort of spreads out along here. This is using AirMod, which has some issues in that it doesn't get the wind dynamics in the valley probably quite right. You can see it's trending in the right direction, but the area with the high concentrations in the east end of the city is sort of over here, so it's not quite aligning perfectly. But we do know that these industrial sources tend to spread out over big chunks of the area and can drive some of the high concentration events. All right. So what I want to do with the time remaining is I want to come back to this picture. And so I'm really proud of this because we worked really hard to make this. But it's static, right? It's a picture. It's our best guess at the annual average. But it doesn't give us anything about temporal resolution, right? We could maybe like modulate the strength of the plume layer to reflect traffic changing throughout the course of the day. But this doesn't tell us anything about if the wind's from the south one day or the north another day. This isn't really giving us that sort of information. And so what ideally we would like to do is, instead of having this as a concentration field, let's say this was an emissions field and we could put it into some chemical transport model. And so the last thing I'm going to talk about is a little bit of inventory building that we've done. And this came out, this is actually an interesting chance we had to do some measurements concurrent with an art exhibit. So there's this artist who goes around, and the art exhibit is called Particle Falls, and the idea is they're trying to make PM visualized. So they project this waterfall into a building, and when PM levels change, the color of the waterfall changes. And they called us up and said, hey, can you help us set this up? And we said, yeah, as long as we can put some of our own instruments in your little tower there. So we were measuring right here, and it turned out to be a good location to sample emissions from the bus fleet because there's a bus station sort of right here off camera. And so for about a month, around this time last year, we measured black carbon, we measured PM 2.5, and we measured CO2, so we can convert things to emission factor. And for about a 10-day period during there, we had a video camera pointed at the street so we could identify whether what type of vehicle is passing the site. And so once again, we can see that this data has lots of discrete spikes, and some are quite large and some are smaller. And so we can analyze them using the same sort of methods that I showed a while back, where we're pulling out plumes from the background. But in this case, we really want to focus on the plumes. And so one thing we can do is we can look at, again, we're looking at black carbon. Now we're looking at a typical diurnal pattern and apportioning it between sort of three main categories. One is there's this regional background that I've shown that's around 0.5 microgram per cubic meter. That's the lowest concentrations we see in the city center. It's also what we see when we go out to sort of the further out suburbs. And then on top of that, the concentration modulates over the course of the day. It tracks very well with traffic intensity and then also the frequency of buses at that nearby bus stop, right? So we get a peak at about 7 or 8 a.m. We get another peak at around 5 p.m., right? So this is driven by traffic in the downtown area. And we can separate that between these short-term plumes, which are basically individual captures of buses as they drive by, which are about 8 to 10% of the total black carbon averaged over the course of a day. And then the rest, what I'm calling this local enhancement, is basically the result of all the other traffic that's happening in the downtown area. Because we measured CO2, we can pull out emission factors for all of this. So this is a histogram of emission factors in gram per kilogram for each of these buses. We identified 281 unique plumes. The bus fleet has something like 600 buses in it. I'm not saying we had 200 buses. Unfortunately, the camera was good enough for us to tell the difference between a bus and a truck, but not good enough for us to read the tail numbers of the buses. So we probably have some buses that we sampled more than once. Our mean emission so our bus fleet actually is a little bit on the older side, so more than half are pre-2007, before they had to have particle filters in them. And so what we see is that our mean emission factor from the fleet is a little bit higher than sort of the current standard, which is roughly around where this blue dashed line is. We see some of the buses are highly emitting. Note this is again as a log scale, and then a few are really clean. So a couple of these are sort of diesel-electric hybrids that are very new. And so something we can do with this is we can use this to build an emissions inventory, right? So the buses run on a fixed schedule, so we know where they should be and when they should be there. So we know, and we know the length of each route. So it's pretty, with some, you can assume fuel efficiency to go from miles driven to gallons of fuel burned, or kilograms of fuel burned rather, and we can then convert that to emissions of black carbon, and then use GIS to create a gridded inventory. And so this is what the inventory looks like in sort of a zoomed out view. So the darker colors indicate higher emissions. This is kilograms of year black carbon just from the bus system. I will point out one of the things, when you say diesel, most people think about trucks on the highway, but buses operate where people live, right? So this is a case where you can have sort of, higher sort of relative exposure because the buses are where the people live. So most of the buses are running, in the center of the county, near the city, and then as you get further out, the density of the bus traffic goes down. So we can zoom in this a little bit. You can see when we're downtown, there's a lot of activity, also sort of out towards where our campus is high activity, and then as you go further out, it falls off. And so this is appropriate for inclusion in the chemical transport models. When I brought this up to my colleagues who do the modeling, they said, yeah, we'd be interested in that, but you need trucks and trains in it as well. So those are things we're interested in perhaps looking into in the future. But you could also, this has value on its own. So we could think about aggregating all the emissions in each census block or census tract and looking at sort of the total impact in each of those census tracts. So this was Tim Dahlman's work, and when he presented it, he threw up, you could think about having, planning the bus, deploying the higher emitting buses out in areas with lower population density, which is sort of fraught with controversy because the lower population density areas that the buses serve are also the lower income areas, so maybe don't want to do that. I'm going to end here with the four sort of points that I started with. I've shown that there are pretty big spatial variations in these different pollutants. For black carbon, it was something like a factor of 3 or 4 over a small spatial scale. For benzene and toluene, it was a factor of 2 or so. And the different pollutants vary differently spatially, and that's a consequence of the sources that are driving the emissions. I showed a few slides where we looked at how these exposures can manifest themselves in differential health impacts. There are certain parts of the county, especially near rivers, that are sort of basically worse to live than sort of the higher up areas. And again, we got a lot of good data from the mobile sampling to get the high time resolution, and we had to sort of put more thought into sort of averaging that out to an annual level. And I think more broadly, what we've learned, we learned a lot of stuff specifically about Pittsburgh, but I think in terms of processing the data, that is perhaps more applicable, to sort of future studies in other cities. So thanks, and I hope everyone has some questions.
Spatial resolution from a transportation perspective, it's laughably coarse. This number of permanent sensors you have is really very few for a whole metropolitan area. What kind of spatial variation is there actually in pollution? It seems to me it's very high because you're measuring the spikes from individual vehicles, and yet you're measuring them at a very small number of places within the metropolitan area. How can you actually be drawing conclusions?
Right. So I guess I should qualify. From our perspective, high resolution is going to be on the order of a kilometer, which
seems really coarse when you're picking up the indications of an individual vehicle.
Right. And so you have to compare that to sort of the current spatial resolution of the monitoring network is, 5 sensors for, I forget how big the county is in terms of square kilometers. And sort of the idea with the statistical model, the land use regression model, is to sort of fill in the gaps, right? And that we know the land use sort of at a higher resolution than we can make our measurements. And then we can use the relationships we build between our measurements and the land use and fill in those different spots. But we're never going to be able to get totally, there's some practical limit to how densely we can monitor, right?
I mean, of course there is a limit. And I guess the question is, has anyone done an analysis of what the benefits and costs in terms of resolution are, and to push for a network of, a much finer network of sensors than what's out there today?
So people have looked at sort of and Julian might know the numbers better than me off the top of my head, how many sensors you need in a certain sort of specific area, like at what point you sort of roll over and sort of max out your, basically your predictive power. Speaking to the distributed sensors, that's very much sort of an active area, so that we're trying to get into some, in Chicago they're going to deploy 500 sensors over the next 3 years. And that's sort of far and away the largest deployment that I'm aware of. I know there are a lot of other cities that are shooting for, several tens of sensors that are permanent and then trying to build on that. But these, then they have to be lower cost and they're inherently sort of less accurate, right?
Sure, but if you have a lot of low-cost sensors that might be less accurate individually, in the aggregate they might be more accurate, right? So
yes, and that's the hope. Yeah.
So you described your neighborhoods in terms of industrial and your campus and places where there are houses. People tend to move between neighborhoods through any 24-hour period.
Yep.
How did you incorporate that one? For example, you did your 150 deaths or any analysis where you're trying to draw conclusions that are going to lead to policy changes.
Right, so that's an important concern. So that particular analysis, we just assumed everyone was home all the time, which is not true for a lot of the population, right? Yeah, and so accounting for that, I think, is important, and I don't have all the answers for that. I know how, then you can make that as complicated as you want, right? So like, we are not breathing pure outside air right now, clearly, right? So you have to account for sort of into the building, in our particular model, we get, to sort of make the sort of road edge measurements fit, we have concentrations in the center of the roadway that, the bright red lines that might not be realistic, right? They might not be that number on the roadway. So we would, I think, if we were to sort of track people with GPS, we might be really biased by, this number that we're assigning in the center of the roadway. But yeah, you're exactly right that, most of the epidemiology, what I showed from the Harvard 6 City study, there's been a lot of progress made on just knowing outdoor ambient. And so there's, rationale to keep pushing on that end of it. But yeah, sort of understanding exact exposures is sort of much more complicated.
Do you sample in winter? Do the spatial patterns differ much between summer and winter?
So we did sample in summer and winter, and we did not. A lot of the overall patterns are not different, but the near roadway patterns are stronger in summer. So you get bigger gradients near the roads for black carbon and PAHs in summer than in winter. And I'm not quite sure why that is. But we got it in both phases, so it's not like an artifact of sort of how we deployed or something like that, or the instrument operation. It was, we actually had different instruments.
estimates of the death rates, you showed the spatial variability of that, and it looked like it was maybe zip code level data. Is that the case?
It was census, I always forget this, whichever, census block or census tract, whichever is smaller, which I think is census block.
Well, there's blocks, and then block groups, and then tracts.
So block.
Okay, well, yeah. Okay, so that was my next question. You also looked at exposure as a function of income, and was that done also at the, presumably I was guessing at the block group level?
That was at the individual property level. So we pulled the locations for the individual single-family homes in our phase 1 domain. So we had 200,000 single-family homes in that domain.
But you were showing income levels though.
So, oh, yeah, so we based it on, we found, I think from the American Community Home Survey, there was a pretty tight relationship between fair market value of the home and income. And so that's, yeah, so essentially it was actually fair market value, but that was pretty linearly correlated with income.
Yeah, what we found is that other more indirect measures might be better measures than income, because there are areas, you know, for example, downtown Minneapolis, there are apartments, high value apartments, but there's also a lot of roadways and pollution sources nearby, and so it kind of can mess up that relationship between income and concentrations. But other more indirect measures like property value and spacing out on some of the other ones that we use, but some of the indirect measures, vehicle ownership and method of commuting tended to be more related to exposure. You know, so if you own more vehicles, you actually tend to have lower exposure at your point of residence.
Okay. Cool. Well, yeah, thank you for that. Now, we had that in the initial version of the paper, we had that figure, and the reviewers all said, we called it environmental justice analysis, and the reviewers all said, no. You need to do more on that. So we ended up having to pull it out. But I still think it's a sort of interesting result to show.
All right. I think with that, let's thank our speaker one more time. There's wine and cheese as usual.
Thanks.
So you know Paul.
What's that?
You know Paul Alan Robinson. I wasn't sure if I should mention EPA's here or not, but I definitely.